Hi, thanks for joining me. Today I've got an interesting graph theory video for you. What we're going to be doing is proving a theorem that says that if we have sufficiently many edges to our graph, then we know that it is connected. But in maths terms, that means, well, suppose we have a simple graph G and it has n vertices and little m edges. We want to prove that if m is bigger than n minus 1 choose 2, so in other words, if m is sufficiently large, then G is connected. Okay, if you want to have a go at proving this theorem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the way we're going to prove this theorem is by contradiction. So suppose, for contradiction, there exists a graph G with n vertices and m edges, with m being bigger than n minus 1 choose 2. However, G is disconnected. Well, because G is disconnected, that means that there exist vertices little x and little y, such that there's no path from x to y, and that kind of just follows from the definition of connectivity. Okay, the next thing we're going to do is introduce the connected component of little x. So we're going to call that big X, and that's simply the set of vertices, so the set of little v in our vertex set, v of G, for which there exists a path from x to v. Okay, so this is essentially all the vertices you can get to from x by traversing along these edges. Now we know that little x will be in this set here, because of course that kind of corresponds to the empty path, not moving at all. But we also know that y won't be in this set, because by kind of construction, x and y, there's no path between them, so y won't be in this set. The next thing we're going to do is kind of consider the complement of this set. So we're going to call that x tilde, and this is simply going to be the set of vertices in our graph, but without x. So basically, these are all the vertices you can't get to from x. And we know that little y will be in this set, and of course little x won't be in this set. Okay, so this is just kind of, this guy here is what's known as a connected component of little x, and this is just, well, what's left. And now one thing we're going to state is kind of obvious now, because we know little x is in here, certainly the cardinality of big X is at least 1. But because little y is not in big X, then that means that the cardinality of x must be at most n minus 1. Because it doesn't have all the vertices in, because it doesn't have y in, but it could in theory have all the other vertices, except, y is, say, an isolated vertex. But we know that cardinality of capital X is between 1 and n minus 1, and using a very similar argument, we say that x tilde is also between these bounds. It's bigger than or equal to 1, but it's at most n minus 1. Anyway, this is hopefully kind of straightforward, and hopefully it was quite easy to follow. Let me clean up the whiteboard and we'll continue. Okay, so what we've just done is we've shown that we can take our graph G and kind of decompose it into two subgraphs, namely x and x tilde, and x and x tilde are disjoint, but their union gives us G. Now, because we know the number of edges in G is just little m, we have that little m is the number of edges in x plus the number of edges in x tilde. So m is the number of edges in x plus the number of edges in x tilde, like so. But now if we just go back to what we had here, we just showed that the number of vertices in x and the number of vertices in x tilde is some number between 1 and n minus 1. What we're going to do is just call r to be the number of vertices in x. So we don't know what it is, it's some number, and it's some number between 1 and n minus 1, but we're just going to call it r for now. Now remember, G is equal to x plus x tilde essentially. So G has n vertices, x has r vertices, so that means that x tilde must have n minus r vertices. So we get that the number of vertices in x tilde is simply n minus r. So we have m equals the number of edges on x plus the number of edges on x tilde, and we also have the number of vertices in x is r, and the number of vertices in x tilde is n minus r. The next thing we want to do is just kind of make an observation, and that is the maximum number of edges a graph can have with k vertices. So suppose we have a graph with k vertices, so this is the case, I guess, k equals 6. Well then, what is the maximum number of edges we can kind of put on that? Well, that's obviously going to correspond to the complete graph. So when we connect every vertex to every other vertex, like so. So if we do something like that, so I think that's all the edges on there, but it's very clear to see that that is going to be the way that you put as many edges as possible on this graph. Well, how many edges are there on this graph? Well, it has k vertices, so the number of edges, therefore, is simply k choose 2. And one way to see that is, well, we're going to connect every vertex to every other vertex, so we're considering pairs of vertices and drawing an edge between them. So how many vertices are there? Well, there are k, and for every kind of choice of edge, it corresponds to the 2 n vertices. And how many ways are there to choose 2 vertices from a choice of k? Well, it's k choose 2. Okay, so that means any graph with k vertices has at most k choose 2 edges. But we know x has r vertices and x tilde has n minus r vertices. So that means that the number of edges in x is at most, from this argument here, r choose 2. And for x tilde is n minus r choose 2, like so. So m is bounded from above by r choose 2 and n minus r choose 2. But we can go ahead and write out what this is. R choose 2 is simply r times r minus 1 over 2. And n minus r choose 2 is simply n minus r times n minus r minus 1 over 2, like so. But now we can just go ahead and expand and simplify, bringing everything under 2. We get this is equal to r squared minus r from this guy here, plus n squared minus nr minus n minus nr plus r squared plus r all over 2, like so. Now let's see if there are any sort of simplifications we can do. Well, we've got a minus r here and a plus r here. Okay, an r squared and an r squared, we can bring them together and call that 2r squared. We've got an n squared by itself, but we've got 2 minus nr, so we can bring those together and put a minus 2nr here. So we've got 2r squared plus n squared minus 2nr minus n all over 2. So we've shown that m is at most this guy here, but essentially what we want to do now is show, because we know that m is bigger than n minus 1 choose 2, we want to show that satisfying both of these inequalities here is impossible, and that will allow us to arrive at our contradiction. Anyway, let me clean up the whiteboard and we'll continue. Okay, so we just showed that m is at most n squared minus 2nr minus n plus 2r squared all over 2, and what we want to do is show that it's impossible for m to satisfy both of these inequalities here. Now, one way of doing that is simply by showing that this guy here is at most n minus 1 choose 2. Because of course, if we can prove this inequality here holds true, then we have that m is at most n minus 1 choose 2, but simultaneously it's supposed to be bigger than n minus 1 choose 2, and of course you can't have both of those things hold true at the same time. So we want to prove this inequality here holds true, so what we're going to do is prove this inequality holds true by kind of expanding and simplifying and cancelling down, but notice that each step is reversible, so it will arrive at an inequality which we know is true, and then we can reverse all those steps here to get this inequality here. So we want to show this inequality here is true. Let's just start by expanding this right hand side. N minus 1 choose 2 is of course n minus 1 times n minus 2 all over 2. Then just cancelling the 2's on both sides, so multiplying both sides by 2. We get this thing here. And the next thing we're going to do is just expand the right hand side. So we get n squared minus 3n plus 2. N squared minus 3n plus 2, like so. Then we've got an n squared on both sides, so we can get rid of those. And then what we're going to do is essentially bring all the terms onto our right hand side. So we've got a minus 2nr here. If we bring it onto the right hand side, we get a 2nr. If we take this 2r squared and bring it to the right hand side, we're going to get a minus 2r squared. And then this minus n we've got left on this left hand side, when we bring it across, because we've got a minus 3n here, we can group them together and we'll get a minus 2n. And then of course we've still got the plus 2 on the right hand side, and that's bigger than or equal to 0, like so. So we want to prove that this inequality here is true. Well, of course we can just divide through by 2 firstly. So getting rid of this 2, this 2, this 2, and this 2 here turns into a 1, like so. But then notice here we've got nr minus r squared, but of course we can just factor out the r and write that as r times n minus r. And then here we've got minus n plus 1, and of course that's the same as 1 minus n, like so. And we want to show that this thing here is bigger than or equal to 0. So what we're going to do is just get rid of this guy here for a moment and show that this quantity here is bigger than or equal to 0. And the way we're going to do that is by looking at this guy here. We have r times n minus r. And we can think of that as a quadratic in terms of r. So if we perhaps sketch it, like so, so this is kind of our r-axis. And if we sketch r times n minus r equals 0, well, where does it have roots? Well, it has roots at r equals 0 and r equals n, like so. And of course, because it's a quadratic, it's a negative quadratic, it's going to look something a little bit like that, with its kind of maximum point being at n over 2, like so. But remember from before what R is. R is the number of vertices in X. And we showed from before that that's some number between 1 and n minus 1. So in fact, we only really need to restrict looking at the case between this kind of point here. So if that's 1 and that's n minus 1. So we're only really considering the graph in this region here. And now what we want to do is kind of bound this from below. And we know that R is some number between 1 and n minus 1. And R times n minus R, just by looking at this graph here, this thing here is going to be at most, well, whatever happens when R equals 1. And when R equals 1, this guy here is just 1 times n minus 1. Oopsie daisy, 1 times n minus 1, like so. Or equally, we could have chosen R equals n minus 1, and then we would have got n minus 1 times n minus 1, which of course is n minus 1 times 1, and that of course is the same thing. But anyway, this guy here is bounded from below by 1 times n minus 1, which of course is just n minus 1, like so, just by looking at this graph here. And then of course we've still got this 1 minus n here, but of course minus 1 and 1 cancel, n and minus n cancel, and that of course is just 0. So we've shown that R times n minus R plus 1 minus n is bigger than or equal to 0, and that's exactly what we wanted to do. So if we go back up and reverse all those steps, we'll arrive at what we wanted to do and show that m is less than or equal to n minus 1 choose 2, but also simultaneously we must have m is bigger than n minus 1 choose 2, and of course satisfying both of those things at the same time is impossible. And thus we arrive at our contradiction, and hence we can go back to our original claim, which was if we have a graph G which is connected, has n vertices and m edges, and m is bigger than, strictly bigger than n minus 1 choose 2, then G must be connected. Now before I end this video, I just want to make a quick comment about this bound here. A natural question you might ask is, can we do any better? And the answer is no, because in fact we can find a graph with n minus 1 choose 2 edges but is disconnected. Namely, if we take our graph G, let's look back at the case, say n equals 6, and what we're going to do is essentially just isolate one vertex. So we're going to leave this vertex alone and then connect the rest. So make essentially the rest of it a complete graph. So we get something like this. Okay, then well, how many edges are there in the rest? Well, there are going to be n minus 1 vertices now, and again on this graph here, on this kind of complete graph here, and the number of edges therefore is just n minus 1 choose 2. So we have a graph now which has n minus 1 choose 2 edges but is disconnected. So m here has to be strictly bigger than n minus 1 choose 2 to ensure it's connected, because if it equals n minus 1 choose 2, we can kind of get away with this cheat graph here which is disconnected. And yeah, so this is kind of the best lower bound we can get. Anyway, I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.